After completing this webinar, you will be able to identify the different types of valves in the thermostatic expansion valve or TXV portfolio. Explain the purpose of using a TXV valve in refrigeration systems. Identify the location of a TXV valve in refrigeration systems. Explain the working principle behind TXVs. Describe the design and basic elements of TXV valves. List the possible applications for TXV valves. Here you can see a basic refrigeration system with a compressor, evaporator, thermostatic expansion valve or TXV, and condenser as the main components. The thermostatic expansion valve is mounted in front of the evaporator, with the bulb and external equalizing line mounted on the suction line just after the evaporator. Generally, TXVs are used to regulate the amount of refrigerant liquid being injected into the evaporator. They do this by controlling the refrigerant superheat at the evaporator outlet. As a consequence, these valves are especially suitable for liquid injection in so-called dry evaporators, where the superheat at the evaporator outlet is proportional to the evaporator load. Certain TXV versions can also be used to reduce the superheat on systems with capacity regulation performed by hot gas bypass valves. The TXV portfolio consists of three different families of valves: small TXVs and large TXVs. The small TXV valves that are used for refrigeration units with a power rating of up to 26.5 kilowatts consist of T2 TE2, TU TC, and TD1 valves. The large TXV valves that are used for refrigeration units with a power rating above 26.5 kilowatts consist of TE5 to 55 and TGE valves. In addition to this, two large TXVs, PHT and TRE80, are available, although both are scheduled to be discontinued in 1 or 2 years' time. This is a schematic of a refrigeration system showing what happens with the refrigerant in the four main system components. Firstly, between points 1 and 2, the pressure of the refrigerant vapor is increased by the compressor. Refrigerant leaves the compressor as hot vapor at high pressure. Next, between points 2 and 3, the refrigerant is cooled down in the condenser, thereby condensing, from vapor to liquid. Refrigerant leaves the condenser as a subcooled liquid. Pressure is not changed in the condenser. Then, between points 3 and 4, the liquid refrigerant expands because of the pressure drop in the throttling device, thereby dropping in both pressure and temperature. Refrigerant leaves the throttling device as a mixture of vapor and liquid at low pressure. Finally, between points 4 and 1, the refrigerant is heated in the evaporator, thereby evaporating, the remaining liquid to vapor. Refrigerant leaves the evaporator as superheated vapor. Pressure is not changed in the evaporator. As mentioned in a previous slide, the throttling device, from now on called thermostatic expansion valve, controls the superheat at the evaporator outlet point. 1. Because the compressor can be damaged if liquid enters it through the suction connector, it's important to always maintain a certain minimum level of superheat in front of the compressor. The simplest way of doing this is to use a fixed throttling device, such as a capillary tube. This is typically done in, for example, household refrigerators and in other simple systems where optimization is not a selling point. A fixed throttling device can, however, only be effective for one set of operating conditions. This is where the TXV has a huge advantage. Because the TXV is a modulating valve, it will regulate the injection of liquid refrigerant in the evaporator in proportion to the actual operating conditions. This means it prevents liquid passing to the compressor independent of operating conditions. For the expansion valve to operate correctly, it's important to always have 100% liquid in its inlet connection. To guarantee this, it's important to maintain a certain minimum of subcooling in the liquid line. Point 3. If this is not possible, flash gas may develop in the inlet of the throttling device, and this will lead to starvation of the evaporator because of a drop in the injected amount of liquid. The TXV senses the bulb temperature at the evaporator outlet. The bulb temperature is, by means of the evaporating charge, converted into pressure, P-bulb, which through the capillary tube is transferred to the top side of the diaphragm. The evaporating pressure, P-evap, is led to the underside of the diaphragm, either through the external equalizing connector or through a hole inside the valve. Together with the force from the valve mainspring, F-spring, the two pressures achieve a pressure balance which represents the requested superheat, or SH, at the evaporator outlet. Depending on the actual SH value, the TXV orifice will open or close. If the load on the evaporator increases, the increasing superheat will in turn increase the bulb temperature or pressure. This will open the TXV orifice, so more refrigerant is injected. If the load on the evaporator decreases, the decreasing superheat will in turn decrease the bulb temperature or pressure. This will close the TXV orifice, so less refrigerant is injected. In this slide, you can explore the way the TXV valve works. Click on the gray button in the bottom right corner to start the animation. Superheat in relation to the TXV function is a combination of two values or parts. The first part of the superheat is called static superheat, or SS. This is the number of degrees of superheat needed for the valve to overcome the closing force from the TXV mainspring. SS is measured at the TXV bulb position. An SS of 0 degrees would mean that the last part of the refrigerant liquid is evaporated at the bulb position. Ideally, in order to help prevent liquid passing the TXV bulb and ending in the compressor, the SS value should be around 2 to 4 degrees. This would mean that the last liquid is evaporated before the refrigerant reaches the TXV bulb. The second part of the SS is the opening superheat, or OS. This is the number of degrees of superheat needed for the valve to actually open and start to inject refrigerant into the evaporator. The combination of the two superheat values is referred to as operating superheat, or OPS, or total superheat. This value is what the customer or fitter can measure on their refrigeration system. The OPS can be changed either by adjusting the SS or by selecting a larger or smaller orifice. However, once the valve has been mounted in the refrigeration system, only the SS can be adjusted. The OS is fixed in the TXV design. Here you can see some general features and benefits of the thermostatic expansion valve. Constant and proportional injection regulation, compact design and little need for specific mounting, 100% helium test in factory, easy adjustment of superheat, reliable delivery service. Danfoss offers worldwide sales and technical support for the entire product portfolio, as well as a complete range of products, not to mention high-tech diaphragm design and production equipment. The T2 TE2 thermostatic expansion valve is designed with an exchangeable orifice in the inlet connector. The outlet connector is available in either SAE flare or inch or millimeter solder. The valve body is brass, and the diaphragm housing, capillary tube, and bulb are made from stainless steel. This valve has been in the market for more than 40 years and is widely used. In this slide, you can explore the way the T2 TE2 valve works. Please click on the function button in the bottom right corner to start the animation. Move the slider between low and high load to see what happens when the load on the evaporator changes. Here you can see some general features and benefits of the T2 valve. Exchangeable strainer or flare cone on inlet. 8 sizes of interchangeable orifices. Correct capacity size can be chosen. Orifice assembly with stainless steel cone. Large temperature and application range. 6 charge versions, range or MOP. Valves for special temperature ranges can be supplied. Stainless steel bulb and optimized bulb strap. Design protected valve design. The TU-TC thermostatic expansion valve is designed as a completely hermetic valve with easy to solder bimetal connectors. Only solder connectors are available. The entire valve is in stainless steel. The valve was introduced to the market in 1995 and is particularly used in ice cube machines and transport refrigeration. The standard version has a fixed orifice, but a version with exchangeable orifice is available. In this slide, you can explore the way the TU-TC valve works. Please click on the function button in the bottom right. Move the slider between low and high load to see what happens when the load on the evaporator changes. Here you can see some general features and benefits of the TU-TC valve. Complete stainless steel design. Laser welded techniques used in many places, for example, diaphragm and capillary tube. Lightweight, no brackets required. Strainer with high dirt retention capacity. Flexible superheat adjustment due to advanced element design. Advanced charge technology, no mechanical friction in the valve. Bimetal connections. Stable regulation, high COP, and less dehumidification. Works with all common refrigerants, including R410A. Angle and straightway versions, internal or external equalization, factory set superheat. Stainless steel bulb and quick-to-use optimized bulb strap, fast and easy to install. Hermetic design, less material used for valve body. The TGE thermostatic expansion valve is designed as a hermetic valve with copper connectors. Solder SAE flare. Here you can see some general features. The TE5-55 thermostatic expansion valve is designed as 3-component take-apart valves, thereby facilitating flexible installation and easy service. For TE5, both SAE flare and solder connections are available. For TE12, 20, and 55, only solder versions are available. The valve type was originally introduced to the market more than 40 years ago, but has been updated a number of times, most comprehensively in 2011. In this slide, you can explore the way the TE5-55 valve works. Please click on the function button in the bottom right corner to start the animation. Move the slider between low and high load to see what happens when the load on the evaporator changes. Here you can see some general features. A throttling device is necessary in all refrigeration applications. In the most basic systems with little demand for optimization, a capillary tube may be used. However, as soon as optimization of energy or function is necessary, a thermostatic expansion valve, TXV, is used. These valves are typically used in a wide range of refrigeration applications. On the following slides, a selection of some of the possible applications is shown. The slides are divided into the following groups: commercial refrigeration, residential AC and heat pumps, commercial AC, and food retail. Typical applications for expansion valves in the commercial refrigeration section include glass door merchandisers and vending machines, milk tank cooling, transport refrigeration, for trucks or trailers with temperature control, containers, and railway refrigeration, along with compressed air dryers, industrial kitchens, and cold rooms. The expansion valves typically used for commercial refrigeration are T2, TE2, TU-TC, TGE, and TE5-55. Typical applications for expansion valves in the residential AC and heat pump section include residential AC units with or without heat pump functionality, air-to-air heat pumps, and sanitary hot water heat pumps. The expansion valves typically used for residential AC and heat pumps are TU and TD1. Typical applications for expansion valves in the commercial AC refrigeration section include AC rooftop units, bus or railway AC systems, and chillers for large AC systems and process cooling. The expansion valves typically used for commercial AC refrigeration are T2, TE2, TU-TC, TGE, and PHT. Typical applications for expansion valves in the food and retail section include display cabinets for vegetables, fruit, and unpackaged meat and similar products, sales counters for various foods, and reach-in cold rooms for dairy products. The expansion valves typically used for food and retail refrigeration are T2, TE2, and TU.